Click the bell icon to get latest videos from Ekeeda.
Hello friends, so today's session of this video is high pass filter. In high pass filter, we will carry two kind of filters. First is passive filter with passive network and active filter with active network. This is the circuit which is nothing but passive high pass filter. Keep this in mind that whenever your capacitor is in between your input and output in series, that is nothing but your high pass filter. So only one capacitor, one resistor that plays with first order high pass filter when resistor is in shunt and capacitor is in series with respect to input and output. So let's play mathematically how this circuit will call as high pass filter. I want to know that what is the ratio of output to input, that means what is the gain, and we want that gain variation with respect to frequency. So we want gain versus frequency. So if frequency is high, then gain has to be high. For low frequency, gain has to be lesser and lesser. Then and only then I can call this circuit as high pass filter. So we will use voltage divider rule, that is VDR, to get the value of VO in terms of VI, so that we'll get the value of VO with respect to VI. And this is all in frequency domain. So more specifically we will write it as VO, which is function of frequency, VI, which is function of frequency, and that function of frequency is due to one element, that is capacitor. So here we will be getting RSC divided by 1 plus RSC. We will put S is equal to J omega. This is because we are playing with AC signal. That means for sinusoidal signal we just put the value S is equal to J omega. We neglect the real part of it because this sinusoidal signal has only imaginary poles. So that is why we are putting S is equal to J omega. If you are putting S is equal to J omega, then we will be getting VO, which is function of J omega, divided by VI, which is function of J omega, is equal to J omega RC divided by 1 plus J omega RC. Further, we will investigate by just having a denominator and nothing in the numerator. So this will become, I will just manipulate mathematically here and there, and we will be getting this J omega RC I will take at denominator of the denominator. Then this J omega RC को मार डालेगा and we will be getting 1 upon 1 plus 1 upon J omega RC, right? So I'm writing over here J omega RC divided by J omega RC. I'm dividing both numerator and denominator by J omega RC. Then we will be getting 1 plus J omega RC in bracket divided by J omega RC. Simple चीज है. So I will apply here. ये दो एक दूसरे को मार डालेंगे and then we will be getting 1 upon 1 plus 1 upon J omega RC. Clear? And this is now gain, which is nothing but function of frequency. Now we have to determine that what is the magnitude of the gain with respect to change in the frequency variation. Then we will say magnitude part is AJ omega mod is nothing but, we will say here 1 as it is, and here we can say that प्लस का माइनस हो जाएगा if we take this j at the numerator, right? Then we can say that 1 का square plus, but magnitude is as it is, plus 1 upon omega rc the whole square, and it's in square root. It's in square root, and this is nothing but your magnitude part. Now when we are looking for the variation of the gain with respect to frequency, actually we are plotting Bode plot ka magnitude term. Now we will take the variation with respect to this omega, variation of gain with respect to this omega, and we will get to know that this will really work at high frequency. Let's take case by case. If we treat this as omega is equal to 2 pi f, 1 upon square root of 1 square, that is 1 only, plus 1 upon 2 pi f into rc the whole square. Okay, and now I will put something different. I have this frequency which is varying. I wanted to know that at what particular point of frequency I am getting higher magnitude wala gain. So I will decide that this is 1 upon 2 pi rc is nothing but one particular frequency which is constant if r and c is constant. So all the elements in my circuit, the value is constant, then we will be getting this 1 upon 2 pi rc. rc is nothing but the time constant. Then we will be getting 1 upon 2 pi rc is nothing but frequency, right? So I will make some modification. A of j omega ka magnitude is equal to 1 upon square root of 1 plus f, let's say h, which is nothing but 1 upon 2 pi rc, divide by f, which is variable, the whole square. We will write this as where fh is equal to 1 upon 2 pi rc, and that is called as cut off frequency of first order passive high pass filter. I have specified each and everything over here. Cutoff frequency fh, after which we will be getting stable value of magnitude of gain. This is first order. This is because only one RC circuit is there and the transfer function ka power of S is only 1, and that is why we are getting the first order. Passive because we are having only R and C, no active device are there in the picture of the circuit. We will decide what are the cases we are looking for. If F is with respect to FH, if F is less than FH, then what's the variation in the gain? If F is much greater than FH, then what is the value of A? If F is equal to FH, then what will be the value of gain? And that's how we will be getting the variation of the gain with respect to frequency. Let's treat case number A, which is nothing but F is much less than FH. F is much less than FH. Now I can say that if this is so, then this FH divided by, then FH divided by F is much greater than 1. I can also make a statement that 1 is much less than FH divided by F the whole square. Is that clear to you all? Right. If this is so, I can neglect this one part, right? And we can make a statement that then neglect 1 in denominator So your transfer function becomes A of j omega ka magnitude is equal to fh upon f ka square, uska square root. 1 is neglected over here. So we will be getting f upon fh only. F upon fh. Now here I will get to know that if f is decreasing, then the value of this gain will also decrease. If f decreases, A of j omega decreases, and that is nothing but the first case. I will mark this as number 1. We will treat case number B, which is nothing but your frequency is much greater than fh. Then what will happen? If f is much greater than fh, then I can make a statement that this 1 is much greater than fh by f. इसका ही meaning fh by f is very less than 1. Then the square of this is very less than 1. This is because 0.5 is less than 1, but uska square is 0.25, which is very less than 1. Then I will play with this square, fh upon f the whole square. Now which quantity I have to neglect? If this is very less than 1, then I can make a statement that I will neglect this part. So here I will make a conclusion that fh upon f I can neglect. Rather, uska square I will neglect. If I neglect this fh upon f ka square, then whatever value I will be getting, that is nothing but 1. Just go through the transfer function, neglect the value of fh upon f the whole square, we will be getting 1 upon under root of 1 plus nothing. That means your A of j omega is 1. Clear? Nice. We will understand now case number C. Before going to case number C, we will say that this is equation number 2. In case number C, we will find out what is the exact value of gain at exact frequency f is equal to fh. So we will write this as f is equal to fh. Now if f is equal to fh, there is no meaning to neglect any part. If f is equal to fh, f upon fh or fh upon f is equal to 1, that is exactly equal to the another term, that is 1 in the denominator. A of j omega now will become 1 upon square root of 1 plus fh upon f will be 1. So 1 ka square is 1. We will be getting 1 upon root 2, and this is nothing but your third value. So case A mein whatever value I am getting, that is decreasing with respect to f. In case B, the value of A is constant, which is maximum, and in case number C, whatever value I am getting, that is less than 1, that is at exact frequency, that is nothing but a cutoff frequency fh. So at fh we are getting gain is equal to 1 upon root 2. Okay, we will try to plot a graph of gain with respect to frequency in logarithmic scale. This is your gain, A of j omega. This is your frequency in logarithmic scale, so as to compress all the frequency, and I put it on one particular A4 size ka paper only. Now we will take case by case. In case A, we have understood that the value of A, which is increasing as frequency is increasing. In another way, I can say that f is decreasing, then your value of A is decreasing. But we are starting from 0th frequency, which is practically not possible. So here, let's say this is 10. This is logarithmic scale. So this is 100 and this is 1000 and so on. We are saying that this gain is increasing as per case number 1. So this is increasing and increasing linearly. So we will say that this is case number A. As frequency increases, your A increases, and at particular value, let's say this is particular value, according to the value of R and C, we will be getting the value of FH, because FH is equal to 1 upon 2 pi RC, and this is, let's say, FH, which is equal to 1 upon 2 pi RC, and after that FH we will be getting the constant value. So this is case number C, where F is equal to FH, and we will take this projection on y-axis such that the value is A divided by root 2, and here value of A, that is AM, is 1, right? Here we will say this value is 1, and that 1 will get appeared in case number B. In case B, we are getting maximum value of gain, that is A, is equal to 1, and that is why we are getting the value of gain at F is equal to FH is equal to A by root 2 in general. So if gain, maximum gain is non-equal to A, suppose 10, then 10 by root 2 will be your gain at your cutoff frequency. Now looking at this particular graph, can you get to know that yes, this is something called as high pass filter, which is allowing my signal to pass if it is of high frequency, which is greater than obviously FH, so that we can determine the signal which are greater than FH or not. I will pass those signal only, and I will not allow to pass the signal which are less than FH. Will attenuate those signals. Practically, these are the practical waveforms. Ideal waveforms are abrupt in nature, but practically it is not possible. Now, how to get the accuracy? How to get accuracy? Accuracy will increase if I increase the order. If order increases, then slope increases. If slope increases, then characteristics tending towards ideal one. So for example, if we take this as first order, we will take another order such that slope will get increased and we will be getting the maximum value is 1, but here in case number A, the variations is something different. If we want more ideal, tending towards ideal, then I will again increase the order such that we will be getting the accurate one filter. So to have more and more accurate filter, we have to have the order of filter has to be more. But at the same time, your circuit will become complex and there is a matter of stability of the circuit. So here we have understood the passive circuit ka high pass filter. Now what is the difference between your active circuit ka high pass filter? Nothing is different. Once we are thorough with the passive circuit ka high pass filter, we can easily draw the active circuit ka high pass filter using operational amplifier. What we will do? We will say, give the heading high pass filter using active device, and that will be treated as active high pass filter. This is resistance R1. This node is coming towards the inverting terminal of operational amplifier. This is your RF. This is VO, RF. This is coming to ground, and here we will apply the passive circuit, which is called as high pass filter. input is given over here. So whatever value we are getting, let's say this is VO1. And according to the virtual ground concept, whatever value we are having here, that will be same over here. So according to the non-inverting amplifier ka gain, we will be getting the value of gain A j omega is equal to A0 divided by under root of 1 plus fh upon f the whole square. Now instead of 1, only the change is here I will put A0. Now question arises, what is A0? A0 is nothing but A0 is equal to gain of non-inverting amplifier, and that is nothing but 1 plus Rf upon R1. So as far as design perspective is concerned, we can easily determine the value of C and value of R if the cutoff frequency is given. And once cutoff frequency is given, one more requirement from the customer point of view is nothing but how much gain, how much maximum gain I want. So that is decided by RF and R1 ka ratio. If customer require the value of open loop gain, that is A0, should be equal to 11, then I will say that RF upon R1 has to be 10. So RF is equal to 10k, R1 is equal to 1k. That's how we can fulfill the customer requirement. And this is how your operation of high pass active filter. Thank you so much for watching this particular video. I hope you enjoyed this video, you like this video. If you like, then like, share and subscribe Ekeeda channel. Thank you very much.